Right, we are in the middle of a calculation. We want to determine the general spherically symmetric solution to Einstein's field equation with a dust source. And then we want to specialize this to the case that the dust is collapsing. That we have a ball of dust which we put there and then we let it go and it will collapse towards a singularity. So that's what Oppenheimer and Snyder did in 1939 in their famous paper. So we began by introducing co-moving coordinates. And we have seen that in these co-moving coordinates, the metric takes the following form. We have our coordinates are tau, rho, theta, and phi. For a certain reason, I do not use r for the radial coordinate, but rho. So, and we have a function, which I denote y, in front of the angular part, d theta squared plus sine squared theta d phi squared. That was a metric. So the essential thing was that we could make this factor equal to minus c squared, so that this coordinate is actually proper time along the tau lines. And the tau lines were chosen such that the dust is moving in this direction. So our forward velocity of the dust was just delta beta tau. And our energy momentum tensor, let me write it with the upper indices. I shouldn't use nu. Let's say beta gamma is the mass density, u beta, u gamma. And what we want to do is we want to solve Einstein's field equation, r beta gamma minus r half g beta gamma is kappa t beta gamma. So that's a program for the next 1.5 hours. So, of course, you have to calculate the curvature quantities from this metric. As I said, I don't do this on the board, so I assume that everybody knows how to do this. So, as I said, usually one does this with the help of a computer program. One has done it once or twice by hand. And then what you get is, well, basically there are 10 equations, right? Beta and gamma take values 0, 1, 2, 3. So we have 10 equations. Fortunately, several of them just give the identity 0 equals 0. On the right-hand side, we have only one component, namely the tau component, which is tau component, which is different from 0. So we have many zeros on the right-hand side. And now let me just write down the components which are non-zero. The tau component is one of them. So this becomes a little bit long, unfortunately, but we have to go through this. So the unknown functions are lambda and y, right? So we expect a system of partial differential equations for these two functions. And also the mu, of course, will occur on the right-hand side. So we have partial derivatives of y and of lambda. So here's the tau component. This is minus 2 over y. d2y d rho squared plus 1 over y d lambda d rho dy d rho minus 1 over y squared dy d rho squared, and this bracket is closed and we have e to the minus lambda plus 1 over c squared y dy by d tau d lambda by d tau plus 1 over c squared y squared dy by d tau squared plus 1 over y squared is 0. That's the first non-zero component. And the second one is a rho component, minus dy by d rho squared, 1 over y squared e to the minus lambda, plus 2 over c squared y, second derivative of y with respect to tau, plus 1 over c squared y squared dy by d tau squared minus 1 over y squared is 0. Sorry, this is a plus, right? Yes, the last one is a plus. So what else do we have? Then we have the other two diagonal elements, theta theta and phi phi component. They are fortunately equal, so they give the same equation. Minus 1 over y, which by the way is just a consequence of the spherical symmetry. It's always this way. Second derivative with respect to rho plus 1 over 2y dy by d rho d lambda by d rho e to the minus lambda plus 1 over c squared dy by d tau d lambda by d tau 1 over 2y plus second derivative of lambda with respect to tau and the factor 1 over c squared plus 1 over c squared d lambda d tau squared plus 1 over c squared second derivative of y and the y in the denominator d tau squared is 0. Okay, and the only non-diagonal element, which is non-trivial, is a tau rho component. This is fairly short, fortunately. Minus 1 over cy d lambda by d tau dy by d rho plus 2 second derivative of y d tau d rho is 0. Okay, let's give names to these equations. Let's say this is F1, F like field equation, F2, F3, and F4. Wait a minute, I made a mistake. This certainly cannot be a 0 in the tau-tau component. You should have protested. In the tau-tau component, we should have the mu on the right-hand side. So this must be kappa mu c squared. Oops. So that's the only equation where I have a non-vanishing right-hand side. Okay, and that's the system of equations we now have to solve. We'll take some time. Okay, how to begin? Well, usually you look which is the simplest looking equation, and you begin with this one. This is a mixed component, right? That's by far the shortest. So let's begin with this. Let's begin with F4. Well, y of what do I have? I forgot the denominator here. Yes, c times y. So c is not 0 anyway, and y is also supposed not to be 0, because if y would be 0, the metric would be degenerate, right? We don't want to have this. So y is non-zero, so we can safely multiply the whole equation with y. By the way, you see from this expression, you read what's the geometric meaning of the y. The y is a radial area coordinate. Yeah, this area of a surface, rho equal constant, tau equal constant. The area is 4 pi y squared. You can read it from this expression. So the y plays here the same role as the r coordinate in the standard Schwarzschild solution. And actually that's the reason why I use a different symbol, rho, here for the radius coordinate, so that we should not confuse it with the Schwarzschild r. Okay, let's begin with F4. So we multiply with c times y, and then we solve for d lambda d tau. What do we get? D lambda d tau is 2 times second derivative with respect to tau of the mixed derivative, d tau d rho, divided by dy d rho. You see, if we multiply this expression with dy by d rho, then we get a derivative in the numerator. Yeah. Now it is just a derivative calculated with the product rule. It's a derivative d by d tau of dy by d rho squared. See, if you calculate this, you get 2 times dy by d rho, 2 times dy by d rho, and then the second derivative of y, the mixed derivative, d tau d rho, which is this here, divided by dy d rho squared, that's a 2. And that's a logarithmic derivative, right? So we can write this as d by d tau log of dy d rho squared. Fine, now we have on the right-hand side a tau derivative, on the left-hand side a tau derivative, so we can integrate this equation immediately. So this implies that d by d tau, let me write everything to the right-hand side, then I have minus lambda plus ln dy by d rho squared is 0. Well, and if the derivative with respect to tau is 0, this means that this thing is a function of rho only. Yeah, rho and tau are our coordinates. So we have that this is a function of rho alone. So if this is a function of rho alone, then also the exponential of this is a function of rho alone. So I exponentiate the expression in the bracket, and I get e to the minus lambda dy d rho squared. So this is a function of rho alone. That's what this equation tells us. And I write this in a funny way. I write this as 1 minus epsilon f of rho squared. Well, the reason is that I know that the solution will behave differently depending on the sign of epsilon. So I have, of course, to allow that the epsilon is 0, plus 1, or minus 1. So this is a general solution on a certain interval of this partial differential equation. Right? If this expression happens to be equal to 1 on a certain interval, then I choose epsilon equal to 0. If it is not equal to 1, then it must be either smaller than 1 or bigger than 1. So by choosing the sign of epsilon appropriately, I get on a certain interval then a solution. How far this interval extends is another question. We have to see later how far we can extend the solution. So we can now solve for lambda. So e to the lambda is then just, this comes on the right hand side, so I have dy by d rho squared, divided by 1 minus epsilon f of rho squared. So what have we achieved now? We've achieved that if we determine y as a function of rho and tau, then this equation tells us what the lambda is. It will depend on an integration constant. Yeah, the f of rho comes into the game as an integration constant in quotation mark. Yeah, the constant depends on rho because we have just a partial derivative with respect to tau. Yeah?
I have one question. Why is there f minus 1 before the epsilon? Doesn't it not really matter if we choose plus or minus 1, or is there any specific reason?
Why I choose a 1 here?
No, the minus epsilon, plus. You would also get that we have epsilon 0.
Yes, yes. This minus sign here.
Yeah.
Of course, I could also write plus epsilon. Yeah, then these two cases would just interchange the rho. This is just a convention. Well, the reason is that we will get an expression which, at the time when Tolman did this calculation, actually, what we are doing now is we are solving the dust equation, the field equation with the dust, for an arbitrary spherically symmetric situation. And the first person who did this was Tolman in 1934. And at this time, similar solutions had already been found, and they involved this factor epsilon in this form. So he has written this in this form just to adapt to this solution which were already known at this time. These were the Friedmann solution. The Friedmann solution which will come out as a particular case here. I will mention this later. Okay, so here we have our first equation. Let's call it G1. This is the equation which gives us a lambda as a function of rho and tau if we have achieved to determine the y. So what is left is we have to determine the y. How do we do this? In order to determine the y, which equation do I choose now? Let me look. F2. So I insert this expression for e to the lambda. Insert this expression, which I call G1, into F2. And if I do it correctly, then the lambda will drop out. Let me see if I manage to do this. So here, this derivative, this is exactly the expression which we have calculated, right? Second derivative of, first derivative of y with respect to rho squared times e to the minus lambda. That's exactly this expression which we have here. So this is, there's a minus sign in front of everything. Let me write it here. Minus 1 minus epsilon f of rho squared times e to the, times 1 over y squared. So that's the first term, this term here. And the other terms I just copy 2 over c squared y second derivative with respect to tau 1 over c squared 1 squared dy d tau squared. And the last term is plus 1 over y squared. And very conveniently, this term cancels against this here. And I multiply the whole expression with, say, minus y squared. Then I have minus epsilon f of rho squared. So I have, I take this to the other side and I multiply it with minus, so I get the same signs as I have here. So I have 2 over c squared y, second derivative with respect to tau. Oh, I multiplied with y squared, sorry. So the y is in the numerator now. And this y squared cancels, 1 over c squared dy by d tau squared. So this equation has a very nice property, namely it involves derivatives of y only with respect to tau. So although it involves partial derivatives, it's actually an ordinary differential equation. Yeah? Because I can fix a rho, I can view rho as a parameter. I fix a rho, and then this is an ordinary differential equation for y as a function of tau. And as such, I will now solve it. So view this. So fix rho. View the equation as ordinary differential equation, as an ordinary differential equation for y as a function of tau. Okay, so let me write it in this way with total derivatives. So now the rho is fixed. So I can now use this as total derivatives. D tau squared is 1 over c squared dy by d tau squared. Actually, that's the reason why I consider the equation F2 at this stage and not one of the other equations, because the other ones involve derivatives with respect to rho and tau. So this wouldn't work with F3, with F2 or F3. No, sorry, with F1 or F3. Okay, so that's what we have to solve. And there is a little trick now how to solve this. We substitute say u for the first derivative squared. Do I do it with a factor in front of it? I think so. Yes, 1 over c squared dy by d tau squared. So then we can calculate the derivative with respect to y of u times y. Yeah, I'm now on the real line parameterized by tau. Rho is fixed, rho is a parameter. And on this line I have my function y. Well, and if I assume that this derivative has no zero, which is a generic case, which gives me the generic solution, then I can switch between the parameter tau and the y as I like. So I can calculate here the derivative with respect to y and uy as a coordinate on my real line. So what do I get if I differentiate this? I get u plus plus y du by dy. Okay? So I can handle this in the following way. U plus y. And I remember now what u was. So u was 1 over c squared times dy by d tau squared. And I calculate this here with the chain rule. So I differentiate with respect to tau, and then I differentiate dy by d tau after that. So I get what? I get u plus y 1 over c squared. Okay, let me write it. I differentiate with respect to tau, and then d tau by dy. dy by d tau squared. Okay, so that's u plus y times 1 over c squared d tau by dy. And if I differentiate this, I get 2 times dy by d tau, second derivative. Okay, and this cancels. And now I hopefully have exactly the expression which we have here on the right hand side. Let me check. Is this the same thing? Yes, I should now resubstitute the u. U was 1 over c squared dy by d tau squared plus 2y over c squared second derivative of y, and hopefully that's exactly the right hand side of this equation we want to solve. So this is equal to minus epsilon f of rho squared, and that's a constant for our calculation. Yeah, and that's now written read from the left hand side to the right hand side. That's the differential equation which we can immediately integrate. Yeah, because this is independent of y or tau. So I can treat it as a constant, and then I can integrate it over. And it gives me what? Gives me u times y is minus epsilon f of rho squared times y, and then I have an integration constant, which of course is a function of rho. How do I call this? Let me see. I have to be careful. I think I made a mistake with the c squares. Let me see. Just a second. See you. So let's check if the units are correct. So this factor should have the same units as a u. What is a u? The u is dimensionless. This is a velocity squared divided by a velocity squared. U is dimensionless. So this should also be dimensionless, and I think it is. I think it is. Where was this introduced? Here it was introduced. You see, this is of course dimensionless, and dy by d rho is length divided by length, so it's also dimensionless. I think it's correct. I have a factor of c squared in my notes, but I think it's wrong in my notes. So let me continue with what we have here. And then I have an integration constant, which I call capital F. Of course, it depends on rho. And if we remember what u was, then we have 1 over c squared dy dy by d tau squared, and I divide by y, so I have minus epsilon f of rho squared as f of rho divided by y. So what have we gained? We had down there a second order differential equation for y. With this trick, with the substitution and this calculation, which allowed us to integrate once, we have now a first order differential equation. And this first order differential equation can be solved in elementary fashion. We have to distinguish the case that epsilon is 0 from the case that epsilon is non-zero. So you see, because, well, I knew beforehand that I would arrive at this differential equation and that here the sign of this factor would play a role, so that's the reason why this factor epsilon was introduced. So of course you couldn't expect this before you had done the calculation. So we have to consider two different cases. So let's solve this for epsilon equals 0. I think then it's very simple. Then we have, if I take the root on both sides, 1 over c dy by d tau is plus or minus the root of f of rho divided by y to the power 1/2. And I can take this to the other side, so I can just solve this differential equation by separation of variables. So I have y to the 1/2 dy is plus minus c root of f rho d tau. Well, and even I can integrate this. This is, what is this here? This is y to the 3/2, right? With a free factor. If I differentiate this, I get 3 times y to the power 1/2. So I have to divide by, to multiply by 2 over 3 in order to get this left-hand side. And on the right-hand side, I have plus minus c root f of rho tau minus an integration constant. And keep in mind that we have fixed the parameter rho, so the integration constant will again depend on rho. Yeah? So that's the solution. That's the solution for epsilon equals 0. And let's call this was G1, right? This was G1, the equation for lambda. So let's call this G2a, because we have also to handle the case epsilon different from 0. So this is the solution for y in the case that epsilon is equal to 0. Yeah? We have now an expression for y in terms of two functions which came in as integration constant. And with this result for y, we also have a result for lambda, so we have determined our metric. Yeah? In the case epsilon equals 0. So we have to treat the case epsilon different from 0, meaning plus or minus 1. Oops. Then here, that was our differential equation. So again, we can separate the variables, but it looks a little bit more complicated then. So let's see, how do we do this? I think I take the square root. Yes. Okay, let's do it slowly. So over c dy by d tau is plus or minus square root of f of rho divided by y minus epsilon f of rho squared. Is that the correct equation? Let me check. Ah, no, I was I was jumping ahead. Sorry, because this is a differential equation which you cannot immediately find in a table or something like that. So what we do is we introduce a new time coordinate. We substitute something. Excuse me. Oops. We substitute for the tau a new parameter, new time parameter, which we call eta. The eta is supposed to be f of rho divided by y times c d tau. So I parameterize my solution now with eta instead of with tau. So I insert this into this expression here, 1 over c squared, dy by d tau squared. Dy by d tau is dy by d eta by d tau. That's a tau. And the right hand side is what it was. Plus f of rho divided by y. Okay, I insert this expression. The eta by d tau squared is f rho squared divided by y squared. And on the right hand side I have minus epsilon rho squared plus f of rho over y. So I think I now it looks much better. So I multiply with y squared. And I have minus epsilon f of rho y squared plus f of rho times y. And that's an elementary integral. So I have dy divided by the root of this here. This was a square, right? I forgot the square. F of rho times y. And on the right hand side I have the eta. Square root of this is f of rho divided by c d eta. And that's an integral you can look up in a table, right? It's a second order polynomial under the root, so that's an elementary integral. Yeah, if it were third or fourth order, it would be an elliptic integral, but that's elementary. These are constants. Yeah, these prefactors are constants. So maybe you remember that the solution depends on the sign of the highest order term. In one case you get something with sign, and in the other case you get something with hyperbolic sign. So we have the solution. The solution is what? The solution is y is equal to f of rho divided by 2f rho squared. Wait a minute, I have something different here. Excuse me. It's the same structure, but the factors are different. Did I make a mistake? Y squared. Yes, I made a mistake. I forgot this. Sorry, excuse me. Oh, my goodness. I think this was correct. Let me check this again. So maybe it's a good idea to divide by f of rho squared. So okay, let me do it slowly. Dy by d eta squared is what? Minus epsilon f of rho squared divided by f of rho squared times c squared times y squared. And here I have plus f of rho divided by f of rho squared times c squared y. I think that's correct now. So now I take the square root, and then I have dy divided by minus epsilon c squared y squared is f of rho squared. I could take a c out of the bracket, but that's not relevant. This is d eta. Okay? And now let me write the solution. Oops. So this integral you can look up. It's see. F of O. Did I forget the C here? Up to the factor C, now everything is correct, but I still, yes, I think I forgot to write, no, wait a minute, the eta by the tau, this also brings a C squared, right? This brings a C squared here, and then this goes away. So the C squared is wrong everywhere. Oops, that's it. So, yeah, I was intelligent enough to write the C in this expression, and then it does no longer occur. Okay, now the solution is what? The solution is f of rho divided by 2f of rho squared, little f of rho squared, and then the derivative of a function h epsilon of eta, which is defined in the following way. So we have the two cases, epsilon equal plus 1 and epsilon equal minus 1. And this is eta minus sine eta for epsilon plus 1. And it is hyperbolic sine eta minus eta for epsilon minus 1. This means that the relation between eta and tau, here this involves the y, which we have just found, is now given by f of rho divided by y. Y is this here. Y is f of rho by 2 rho squared h epsilon prime of eta c d tau. And this gives us the h epsilon of eta in terms of tau. Yeah, I multiply this to the other side, and then I get, this is what? This is 2 f of rho squared c divided by f of rho. And now I have again an integration constant, which I denote in the same way as I did in the case epsilon equals 0, namely by tau naught of rho. So this is a little bit the somewhat complicated expression, which I call G2b, which gives us the function y in the case that epsilon is non-zero, is plus or minus 1. Yeah? So this is the expression for y. And of course I have to know what's these are two integration constants. But I have to know what this is, and what this is written here. Yeah? So it gives me the function h epsilon as a function of eta, but it's given in terms of the tau, which is my original variable. So now I have my solution for both cases. Yeah? For the case y equals 0, it was this simple expression down here, which I call G2a. And in the case epsilon plus 1 or epsilon minus 1, it is this expression here, which is a bit more complicated. And with this, we have found the general. Oh, no, we are not yet. We are not yet done. Sorry. So what have we solved now? We started with F4, then we used F2. So we still have two more equations, right? We have F2 and F3. Actually, we have determined our two unknown functions, the function which enter into the metric. We have determined the y, and with the help of G1, which is somewhere there, also the lambda. We have determined the two functions. Now the question is, do the remaining two field equations tell us anything in addition? So I have to insert these results which we have into F2 and F3. And I don't want to do this on the board because it's a little bit long and quite elementary. So inserting G1 and G2 into F, what was the one with the angles? The one with the angles was, no, this was, that was the one we have used already. So then it's this one, F3, yes, that's the one with the angles. Unfortunately, this gives an identity. doesn't give us any new information. Then the only remaining field equation is F1. F1, of course, gives us a mu. Yeah? So we insert y and lambda on the left-hand side, and then we calculate for mu. So inserting G1 and G2 into F1 gives us a mu, and after a little bit juggling around with the terms, we get a fairly simple expression. We get kappa mu, which is a function of tau and rho. Let me write this explicitly. It's just f prime of rho divided by dy by d rho times y squared. I should also write the arguments here if I have them on the left-hand side. Y squared. And this is my equation G3. And now we have solved the whole problem, right? So we have determined the two unknown functions in the metric, and we have determined the mass density. Yeah? So y is known. So y is known for the two cases, epsilon equals 0 and epsilon equal plus minus 1. We have to insert it here from G2. So the metric is now, the metric is what? The metric is, oops. Again with this term, and then we had the term, is it still on the board? Let me see. Yes, here. E to the lambda times d rho squared. And e to the lambda we have calculated here. E to the lambda is this here. This is plus dy by d rho. It's squared, right? Over 1 minus epsilon f of rho squared plus y d theta squared plus sine squared theta d phi squared with y given by G2. G2a or G2b, depending on what epsilon is. So, and mu is determined, the corresponding density, by G3. Okay, and that's what one calls the Tolman solution. It's a general solution to Einstein's field equation, spherically symmetric with a dust. So that's the Tolman solution. It involves three functions which come in as integration constants. Yeah, the integration constants, they are actually functions of rho, of course. So you already know that f of rho, capital F of rho, and tau naught of rho can be chosen arbitrarily. So whatever you choose for these functions, as long as the whole thing doesn't degenerate, gives you a solution to Einstein's field equation.
Okay.
Yeah?
Should it be y squared in front of the...
Yes, of course. Thank you. There's a square missing. Yeah, y is the area coordinate, so there should be a square, of course. I hope yes, I had it here. Okay, so this was the general solution. So this we can now ask, how far does this solution extend? So what is the range of the coordinates? What we are interested in is a particular solution where this is valid between rho equals 0, the center of our star, and rho equals rho naught, the boundary of our star. And then we want to match it to an exterior vacuum solution. Not to exterior vacuum solution, but of course to the Schwarzschild solution. It must be Schwarzschild if we have spherical symmetry. So, but you don't want to do this for this general form. So this is a dust which moves arbitrarily, on the radial lines, so to preserve spherical symmetry, but it may move up and down the radial line as it like. And we are interested in a special solution. And actually, what Oppenheimer and Snyder considered was a case that the mass density, the mu, is independent of rho, that it's homogeneous. Yeah, so that the interior of the star has a constant density. The density depends on time. Of course, the star becomes denser and denser in the course of time, but it should be independent of rho. And now you see that's not so easy to find from this solution. So this solution was known when Oppenheimer and Snyder did their work. The solution was found 5 years earlier by Tolman. And now the problem was how to specify this so that I get a constant mu. You see, it's not so easy. If you set this equal to a constant, then you have to play around what to do with the other quantities so that all the other equations are still satisfied. And yeah, after some playing around, Oppenheimer and Snyder managed to find such a solution, and we will now specify to this solution. By the way, maybe you are wondering that we have 3 functions here. Of course, why do we get functions? Why don't we get integration constants? Well, obviously because we have a partial differential equation. Yeah? Usually you get from a partial differential equation a solution which involves arbitrary functions. The Schwarzschild solution is special because it boils down to an ordinary differential equation by the Birkhoff theorem. But for dust, of course, there is no Birkhoff theorem, so we really end up with functions. And why 3? Actually, maybe if you start thinking a little bit, you would expect that there should be 2 free functions. You could certainly give on an initial surface, tau equal constant, you could give the mass density at this surface, and you could give the initial velocity for the dust. And as it is supposed to be radial, this is a scalar quantity. Yeah? So the initial velocity is a scalar quantity. You cannot play around with directions. The direction must be radial. So you would expect to have 2 scalar functions. And actually that is true. There are only 2 functions which are independent of the choice of the coordinates. The reason is that this form of the metric is preserved if you transform the coordinate rho into itself, into a new radial coordinate without mixing it with the other coordinates. And this freedom, so we have one function as a piece of arbitrariness in this ansatz. And if you subtract this from 3, then you end up with 2 functions. So there are actually only 2 functions in the game. 2 functions with an invariant meaning. And you may interpret this as the initial density and the initial velocity. And now we want to specify this. We want to try to choose these 3 functions in a way that the mass density becomes independent of rho. And I just tell you how this works. A systematic way of approaching this would be to make a separation ansatz. Yeah, to search for particular solutions where the y and the lambda are products, where one factor depends only on tau and the other one only on rho. If you go with this ansatz into the equations and then plug it into the expression for mu, and then you will easily find a solution where mu is constant. And that's what I write on the board now. So it's a special solution to this situation. We will not match a ball of dust in arbitrary motion. We have a special motion where the density is constant. Okay. So the special solution we want to consider is given by choosing f of rho equal to rho. Capital F of rho as a constant, capital A times rho cubed, and the tau naught equal to 0. And let's see what this gives us. We have to distinguish the 2 cases again for epsilon equals 0. So the y is there in the top line on the right. So we get y is what? F of rho, capital F of rho, is A times rho cubed now. And in the denominator, I have that is C. I can't read my own handwriting. No, it's a 2. 2f rho squared. 2 and f of rho is rho. So 2 times rho squared times, oh, this was not epsilon equals 0, sorry. This was epsilon equal plus minus 1. Epsilon equals 0 is here. Epsilon equals 0 is here. Sorry, this was wrong. Let me see. Let me do it slowly. 2/3, 1 to the power 3/2 is plus minus c root of capital F. This is root of a times rho cubed. Tau and tau naught is equal to 0. So that's it. So can I solve this for y? Y is what? Y is, I think I can choose a positive sign here. I square it anyway. Yeah, so here's a root, I square it now. So then the sign goes away anyway. So I have y is, so I multiply, let me see, no, I cannot do it in my head. Let me do it slowly. So this is y to the power 3/2 is plus minus 3c over 2 root a rho to the power 3/2 times tau. And this implies y is, so here's a constant factor. The constant factor, I can disregard the sign now because I square the equation. So this is, what is it? It's 9 c squared over 4 times a to the power 1/3, right? Then comes the tau, the power 2/3, and the rho. So you see y is a factor which depends only on tau times rho. And let me call this factor here k0 of tau. So you see it satisfies a separation ansatz. Yeah, a function of tau only times a function of rho only. Okay, yes, that's the same. Yes, it's the same. And what about the case epsilon plus minus 1? So then I have to look at this expression there. And y is, there's a capital F, which is a times rho cubed, divided by 2 times f rho squared, which is 2 times rho squared, h epsilon prime of tau. And you see again, this is proportional to rho. So this is a factor which depends on tau. Well, it is a function of tau in the end, but I wrote it in terms of eta. So just to stick with my notation, I should write it in this way. But then you should think of eta as being expressed in terms of tau by this relation there, times rho. And that's what I call k epsilon. In the case epsilon is plus 1 or minus 1 of tau. Yeah? Eta is in a 1-to-1 relation to tau. So we see in both cases, have we put our metric in the form a factor which depends on tau times rho. So that was the essential result. I should also write the relation between eta and tau in this case. So in this case, I hope I have the general relation on the board. Oh yes, there it is. There it is. The eta is 2 times f of rho squared, which in our case is 2 times rho squared times c, divided by capital F, which is a times rho cubed, divided by h epsilon prime of eta d tau. Why do I have a square there? Wait a minute. Oops. Actually, I was hoping that the row cancels. F of rows. But this was a square here. I have a row cubed here in my notes. What did I do? But I think it's correct in this way. This is a transformation for constant row, right? And I think it involves where did this come from? Let me check. There's a substitution. It's f of rho divided by y. Did I do this correct? No, I made a mistake here. Here's a mistake, you see? So it says f of rho divided by y. So I have 1 power already in the numerator, and then I get another 2. So I get a 3 here. I get a 3 here. Oops. And then, of course, also here. And that's much nicer, because then I also have a 3 here. So this is now a row cubed, and here it's also a row cubed, and this goes away. So I have just, yeah, that's a relation. That's a relation, and that's correct. That's correct. So if I like, I can integrate this. So I get, I had it there already. I can use this expression here. Tau naught is 0 now. So I have 2c over a tau. So that's the relation between eta and tau. And remember what h epsilon was. It was this function with sign and hyperbolic sign, depending on the sign of epsilon. Okay, so that's our special solution. And the essential thing is that the y has this structure, k epsilon of tau times rho. Maybe you should also write the mu. What was the mu? The mass density. Oops. The mass density is here. Kappa mu c squared. Oh my goodness. So, kappa mu c squared is what? Is f prime. Capital F is here. I think I can differentiate this. This is a times 3 rho squared, right? And in the denominator I have dy by d rho. dy by d rho is k epsilon. Yeah? It's this expression or this expression here, differentiated with respect to tau, and y squared. And y squared is k epsilon of tau times rho. So this is now cubed times rho squared. And you see, that's what I promised. This is indeed only a function of tau. So it's 3a divided by k epsilon, which depends on tau only. That's an a. So our density is a function of tau only. It's independent of rho. So by this choice of the 3 functions, we have indeed achieved our goal of getting a solution where mu is homogeneous, yeah, over the whole body. Of course, it depends on time, yeah, because the ball is supposed to contract. And I'm sorry?
I think there's a cube missing.
Yeah, thanks. There's a cube missing, yes. I hope now it's correct. So our metric can now be simplified a little bit. So G was minus C squared d tau squared. Oops. There is a general expression. There's a general expression. dy by d rho is k. And it is squared. 1 minus epsilon, and f of rho is rho, so just rho squared plus y. Y is k epsilon of tau times rho, and everything squared. d theta times sine squared theta d phi squared. And yeah, depending on what course in differential geometry you have taken, maybe this is a good old friend of yours, which we have on the board. Namely, if we take the k epsilon out of a bracket, we have here in the curly bracket just the metric of a space that was a square of constant curvature. So what everybody should realize is what this is in the case epsilon equals 0. If epsilon is equal 0, then this is just a flat metric. There's a flat Euclidean metric in spherical polar coordinates. If epsilon is plus 1, then that's a 3-sphere, the standard metric on the 3-sphere in particular coordinates. Maybe some of you have seen this before. So it's a 3-sphere, yeah? So S3, the thing which is embedded into 4-dimensional Euclidean space. And if epsilon is negative, then it is the hyperbolic space. Yeah? It's a space of constant negative curvature. And metrics of this form play an important role in cosmology. There they are known as Friedmann solutions. Yeah? They come with a constant density, with a density which depends only on time, but not on the spatial coordinates. So it is a contracting or expanding dust-filled universe if we extend the coordinate rho as far as possible. So then we have a, so let me write it this here, contour Friedmann solutions of cosmology. Just for those of you who have already encountered them. Of course, here we are not interested in the case that the coordinate rho extends as far as possible. We want to cut it off. We want to have a star with a finite radius, and then we want to match it to a vacuum solution. That's, of course, something you do not do in cosmology. Yeah? So that's a different physical situation we want to consider here. And you see that the time dependence of the thing in these co-moving coordinates, which we are still using, is coded in this one function, k epsilon of tau. And maybe it's a good idea to plot this function. So if we plot this over tau, over our tau axis, where we begin at tau equal minus infinity. Where do we have the k? The k is written, well, here is it for, quite explicitly, for k epsilon equals 0. You see it goes with tau to the power 2/3. So if this comes from infinity, it is something like that. Oops, it should go monotonically to 0. And then the whole metric collapses. Yeah, if tau equals 0 is reached, then this metric coefficient y becomes 0. So this thing here becomes 0, which of course means that the whole metric is degenerate and cannot be extended further. There's another branch, a positive branch, but they are not smoothly linked in one universe to each other. So this is epsilon equals 0. Whereas epsilon equal 1 and equal minus 1, it's here this expression. So we now have to remember what the h epsilon was. I think I have erased it. It was a thing with a sign and with a hyperbolic sign. And if you plot this, you see that if you have epsilon equal to minus 1, you get something which goes steeper than the case epsilon equals 0. But if you have epsilon equal to plus 1, and the whole thing comes back. Yeah, this is epsilon plus 1. So, yeah, this is a sign. Yeah, if you plot eta instead of tau, this would just be a sine function, and the sine function is here. It has periodically zeros on the axis. Of course, it could also take here other branches, but they are not connected with each other in the sense that they form one universe. Each of them is a different universe, and they are separated by singularities. So this is the behavior of this function k epsilon of tau. And here you study these functions in cosmology. So you have a universe which is which has one singularity and in the other direction extends to infinity, and you have a recollapsing universe if you have epsilon equal to plus 1. But here we want to consider stars. So what we want to consider is the situation that we have in this diagram where we plot the tau axis. We want to plot the surface of our star. So this metric is this metric which we have written here is valid for this interval where rho naught is the radius of the star. In these co-moving coordinates, that's a constant, and for rho bigger than rho naught and up to infinity, we have Schwarzschild vacuum solution. That's the situation we want to consider. Yeah? So our interior is described by this dust ball, this spatially homogeneous dust ball, and we want to link it to the Schwarzschild vacuum solution. So then, of course, the surface of the star must be a rho line. Yeah? And maybe it's a good idea to plot not rho. This would be misleading because then the surface would be just a constant. So you would have a vertical line here if we plot rho. But rho is in the co-moving coordinates. So actually we have if we measure the surface of the star with a metric, then we would plot this quantity. Yeah? This quantity gives us the surface, the area of the sphere, tau equal constants, rho equal constants, in particular for the surface of the star, and there it would be time dependent. Yeah, because if I fix rho, then this expression depends on tau. So the surface is, if it's really measured with a metric, it is time dependent. And what was the y? Well, the y was the time dependent factor k epsilon of tau times rho. Yeah? So if I plot this, then the plots look very similar to these curves here. So the surface of the star would be, in one case, this here. So this would be the surface of the star for epsilon equal minus 1. It would be something like that for epsilon equals 0, and it would be something like that for epsilon equal plus 1. So epsilon equal plus 1 is a funny star, right? It's a star which explodes. It starts with a singularity, and then it explodes, reaches a maximum radius, and then collapses back. I would say that's not a very realistic model for a star, but actually we don't need to consider the whole branch of this. We can just start here. Our initial condition here at this point, where the vertical is, where the tangent is vertical, and this would mean that we give as the initial condition that the star is at rest. Yeah? So we have it at one moment at rest, we put it there, and then we let it go. And then it would follow, the surface of the star would follow this curve. And this branch would then be irrelevant as a path. We cannot do this with epsilon equals 0 or epsilon equal minus 1. At any finite radius, this has a certain inclination, so it is never at rest. Yeah? So if you want to put the star at rest and let it go from there, then the relevant solution is a 1 where epsilon is equal to plus 1. And that's what we want to discuss now a little bit further. So we would give initial conditions so that epsilon equal plus 1 is so that initial condition is just given at the maximal extension of this solution with epsilon equal +1. Actually, you can easily determine by which parameter tau this is. So this corresponds to, so if we call this here tau m, then we have tau m corresponding to eta, where this here is maximal. And this, in terms of eta, it is a sine function. Whereas a sine function, it's maximum at pi half, right? So where eta is pi half, there tau m has its maximum, or rather minus, because we come from the negative. So this is the time coordinate where the maximum is reached. There we would have to give our initial condition. And this gives us a collapse time, right? Because we have chosen our integration constant such that it's a collapse ends at tau equals 0. So the absolute value of tau m is just the collapse time, which can be explicitly calculated from the relation between tau and eta. And it is finite, of course. So what we do is we give initial conditions in the following way. Here we have our 0 axis. Here is y of rho and tau, that's the area coordinate. Here is tau. And here was our solution for epsilon equal +1. And we give now our initial condition here on this hyperplane, where tau is equal to tau m. So the individual dust particles, that's the surface of the star, that's rho naught, the surface of the star. The individual dust particles start with a vertical tangent. Yeah, so at the moment, the whole thing is at rest, at this moment. And then it follows this equation. We have y as a function of tau. So we really have the word lines of these dust particles. And all of them come together at the event tau equals 0. And so let me write this in another place. Let me write this here. Oops. So, of course, this is now for our exterior Schwarzschild vacuum solution. This is the ordinary R coordinate. Yeah? The area coordinate is the ordinary Schwarzschild coordinate. So somewhere here we have RS, our Schwarzschild horizon. And now you see what happens. At this instant, the horizon is disposed. Yeah? When the surface of the star reaches this point, so at this time, from this time onward, the horizon is exposed. And from this time onward, we have here a black hole. So remember how the light rays behaved in the exterior vacuum, Schwarzschild spacetime. This is a light ray. Yeah? The light ray stays on the horizon. If I emit from the surface a light ray outside of the horizon, then it will go along these curves. And if I do it at a smaller radius, then the light rays will go towards the center. So these are light rays. So you see that from this moment onward, the surface of the star can no longer be seen by a distant observer. That's what we have studied already in the vacuum Schwarzschild spacetime, where we didn't care about the interior solution. So the new aspect is that for this simple situation of a dust, we now really have a metric for the interior. And you may ask what happens inside the star. So for instance, you may ask, is the horizon maybe already forming somewhere before this event? So is the horizon inside the star? That's a question that maybe we could discuss in one of the worksheets. So actually, the horizon does form inside the star. So the vacuum Schwarzschild discussion, of course, allows us only to tell what is outside, but now we have the interior metric. So we can really discuss everything what's going on inside the star. And for this dust, where the collapse takes place in a finite time, and that's the time. There's one piece missing. The exterior Schwarzschild metric is characterized by the mass, the parameter m, which is defined asymptotically, if you remember, right? Here, for our solution, we have this constant a. Yeah, there's the first line. We have this constant a, which occurs in the function capital F of rho. And the question is, how is this a related to the m of the exterior Schwarzschild solution? That's a question we still have to answer. So, and this will give us a quite interesting expression for the density, actually, if we express this a here in terms of the mass, as it is defined asymptotically. So the relation between a and m, where we know that the surface, that a point on the surface moves on a geodesic. It is dust. We have dust. Yeah. All of these curves are geodesic in the metric. So the interior ones, of course, are geodesics in the interior metric, which is written there. But the surface, a point on the surface, this should be matched to the vacuum Schwarzschild spacetime outside. So the surface of the star must be a geodesic in the ambient space, in the vacuum Schwarzschild spacetime. And for freely falling, or let's say for time-like geodesics, radial time-like geodesics, in Schwarzschild, in vacuum Schwarzschild, we have actually derived the equation of motion. We have calculated this expression, and we have found that, wait a minute, that's the velocity, so I should need a 1 over c squared. We have a constant. The value of this constant depends on where our radial geodesic is at rest. So if we drop our particle at rest from a certain radius, this is here's y. From a certain radius, then we get an integration constant which depends on this radius. This is this constant, but the interesting thing was this here, and this was Rs over r. We had shown this, I think, a week ago or so. And now we compare this with our expression for the tau derivative of y. Y corresponds to the r. Y is the area coordinate. Compare with our expression dy by d tau squared. Let me also write 1 over c squared, and y is written there. Y is k epsilon of tau times rho. So this is 1 over c squared, k epsilon prime of tau squared, rho squared. And if we are on the surface, let me see, how do we do this? So I have to write, wherever I read an r here, I now have to write my y. So this would be, in order to compare this with this here, I write this derivative of this, and I want to have a y in the denominator. So I want to write a y here. So y is k times rho. So I have this 3 times rho cubed. And if I evaluate this on the surface of the star, then rho naught is a constant. So this is a constant. And now you see, I have here the expression 1 over my radial coordinate. I here also have 1 over my radial coordinate, and this must be the RS. What is in front of this must be the RS. So we have RS must be 1 over c squared, k epsilon prime of tau rho naught cubed. Oops. So if you remember that this was 2gm over c squared, and we need to know how this is related to the a. Where is the a? Oh, I do it for epsilon equals 0 now, for epsilon equals 0. That's the case which we have plotted there. Yeah? So epsilon equals 0, k naught is this here. K naught is this here. Can I differentiate this? I hope I can differentiate this. So this is 9c squared a over 4 to the power 1/3. And then I have to differentiate this here. This gives 2/3. 2/3. What is 2/3 minus 1? Is minus 1/3, right? I think that's it. What have I done now? There's something wrong. Why do I get a... Excuse me. Why do I get a tau there? Of course, everything should be constant. Sorry. This was the case, epsilon equal 1. Oh, I looked at equation. That's the point. Sorry. Yes, epsilon equal 1, of course, is the case we're interested in. Maybe I do this in a different way. Let me check. How did I do it here? Looks quite simple here. Why is it so simple? I used an earlier expression. Sorry. This was. I think it was correct, but I wrote it in a way that I cannot make much use of it. We had an expression for dy by d tau earlier, which is much more convenient to what we need. So we had an expression dy by d tau squared is, with a 1 over c squared in front, was minus epsilon f of rho squared plus f of rho over y. Yeah, you remember this was even before we specified the f, the little f and the capital F. And now we do this at rho equal rho naught, rho equal rho naught, and now we compare these two expressions. And now we see immediately that the Rs must be the capital F of rho naught. Yeah? This implies that the Rs must be F of rho naught. Because the R, the radius coordinate R in the exterior Schwarzschild spacetime corresponds to the Y. So the tau dependence is only in the Y, and here the tau dependence is only in the R. This is independent of tau, this is independent of tau, so it must be the same. And this is our constant, right? And now we remember what these expressions were. So we have, let me see, f of rho was, did I erase it? No, fortunately not. Here, this was here. So we have 2g m over c squared is a times rho naught cubed. And that's the relation between the constants a and m. Yeah? And the radius, the initial radius is also involved. And if we insert this into the density, then we get something very interesting. So k mu is written down there. K mu c squared was what? 3a over k epsilon of tau. Do I want to have this? Yes. Ah, yes, I can express this now in terms of the y. Yes. So that's my density. So the density is time dependent, of course. The dependent comes over this factor k epsilon. And if I multiply numerator and denominator with rho cubed, say this at the radius, then I have what? I have, and I insert the A. I've just calculated the A. Yeah, this was A times rho naught cubed is this here. So I have 3 times 2gm divided by c squared. And then I have k epsilon of tau squared rho naught cubed. And this is just my y, what I have here. So this is 6 gm over c squared y at tau and rho naught. Wait a minute. Don't I have it cubed? Yes, hopefully it should.
It is down there.
Yeah? Oh, I just copied it incorrectly. That's much better, because then I have this here cubed. Very good. Okay, hope you remember how kappa and g were related. That's another thing we would need. And then we are done. And then we have a very interesting equation on the board. Kappa was 8pg over c to the 4, right? This was kappa, if you remember. This came from comparison with the Newtonian limit. Mu c squared. And on the other side, I have 6gm c squared y of tau and rho naught cubed. Let me see if I can solve this from u. I think the c's cancel, right? Yes. And also the g cancels. So I have mu is m, that's the Schwarzschild mass, the asymptotically defined mass, divided by, let me see, 8 divided by 6 is 4 divided by 3, right? Pi y of tau rho naught cubed. Very interesting, right? So the mass density is a mass divided by the volume of a sphere with radius y of tau and rho. I looked this a few hours ago, I looked this equation up in the book by Weinberg, and he wrote, "No surprise!" exclamation mark, right? That was his comment to this equation. I think this is extremely surprising. Yeah? I'm very much surprised by this equation, because this mass was not defined as an integral over the mass density. It was defined asymptotically. So that it has anything to do with an integral over this mu was not to be expected. And even more importantly, this is a formula for a sphere, for the volume of a sphere, of the interior of a sphere in Euclidean space. But we are not in Euclidean space, we are in curved space. I would expect a completely different relation between the radius of the sphere and the volume. So apparently these two unexpected things cancel each other, so that in the end the familiar formula comes up again. But I would not have expected something like that to hold. In my view, it's really very much surprising that this simple formula comes out. But of course, it's easily remembered, right? So the mass density is just the asymptotically defined mass divided by the usual volume. Oh, I'm already over time. So I think I would like to discuss this a little bit further, in particular this picture, and telling a little bit of what's going on in the interior. But I think this will not take more than 15 minutes or so, and then we can move on to other solutions on Friday. Okay, so see you on Friday.